Okay.
Yes.
Yeah, thank you. Okay, so thank you for the introduction. So I'm Yuto Nakashima from Kyushu University in Japan. So today I will talk about on the number of non-equivalent parameterized square in a string. So this work was presented at the Spire conference this year. So this is a joint work with Rikuya Hamai, Kazushi Taketsugu, Shunsuke Hinaga, Hideo Banai. So, okay, so the one of the main contributor is Rikuya Hamai. So he is a first grade master's course in our group. So and now Japan is 11 o'clock in evening. So I'm a little bit sleepy. So I can answer the easy question. So uh, maybe Shunsuke and Hideo is here, so they can help. Maybe. Okay, so let's start. Okay, so everyone here knows what is a square. The square is represented by XX for some string X. So it is one of the fundamental topics in combinatorics onwards. All properties on repetitions are widely used in many fields. So one of the natural questions on squares is how many distinct squares can a string of length n contain? Oh, let's see this example. So in this example, so there are 5 distinct squares. So one is AA and C and AB is here, and the longer square, 2 squares are here. So there are 5 distinct squares. So if we count the occurrences of the squares, so there's a simple lower bound on the maximum number of square occurrences. If we consider length n unary string like this, a to the n, so it has n squared square occurrences. So counting distinct squares is a natural problem. So there was a conjecture for this problem. The maximum number of distinct squares is less than n, and many people tackled this problem and like this. Now recently, this conjecture was proved by Parameterized and Lee. Okay, so again, square can also be introduced as a concatenation of 2 equal strings. So due to this fact, so there is a simple extension of squares. So the question is, what happens if equal is changed from exact matching to another string matching model or equivalence model? So several string matching or equivalence model exists, such as parameterized matching and Abelian matching and order preserving matching and so on. So this is in this talk we focus on the parameterized matching. So I will give the definition of the parameter matching later. So in the Abelian matching, so two same length string equivalent Abelian equivalent if the number of occurrences of each character is the same. So in this example, so this pattern, this substring of length 4 has 1A and 2Bs and 1C. So this CABB also 1A and 2Bs and 1C, so these are Abelian equivalent. So in order of preserving matching, so they are equivalent if the sequence of rank of each character is the same like this. So in this talk, we focus on the parameterized matching. So this is a definition of formal definition of the parameterized equivalence. So two string x and y of length k are said to be parameterized equivalent if there is a bijection f on the alphabet such that the ith character in x maps by f to ith character in y for all positions I. So let's see this example. Okay, so this AABC the, is equivalent to BBAC or an AACB, also CCAB. So because in this case, so this A maps to this B, and B maps to A, and C maps to C zone. And here, so this A is maps to A, and B maps to C, and C maps to B. So there is a bijection like this. So in this case, A maps to C, and B maps to A, and C maps to B. So there is also bijection. So these are parameterized equivalent. And we in this slide, so we write this. We use this notation x equivalent to y if x and y are parameterized equivalent. Okay, next I will explain the parameterized square. So this is the definition. A string W is called a parameterized square when W is equal to xy for strings xy. And these x, y, and x and y are parameterized equivalent. So let's see this example. So these three substrings are parameterized squares. Okay, so for this string, so ACBB is parameterized equivalent to BACC. So this ACBBBACC is a parameterized square. And so this longer, let's see this longer one. So BCCBA is parameterized equivalent to CBBCA because there is a bijection like this. So this string is a parameterized square. So we sometimes use capital P to denote the term parameterized. So for example, we say P square instead of parameterized square sometimes. Okay, here I will explain definitions of the distinctness of the squares in other equivalent models. So this notion was stated by Nakashima in 2016. There are two types of the distinctness. So first one is the number of p-squares that are distinct as words. And the second case is the number of parameterized squares that are non-equivalent in the equivalence model. So let's see this example. Okay, so we focus on these two parameterized squares. So in the first case, so these are distinct because they are not identical like this. So CABBA is not equal to the AABCCB as strings. So they are distinct in this case. So in another case, they are not distinct parameterized squares because they are not identical, but they are parameterized equivalent, so they are not distinct in the second case. And so for these situations, so Kashima Kaeto first presented several upper and lower bounds of the maximum number of squares in these equivalent models, like this. So later, Gaffrey-Hofsky et al. Gave tighter bounds in the order preserving model like this. Okay, in this talk, we improve this situation. So Kashima et al. So they showed 2 times sigma factorial times n upper bound for non-equivalent parameterized squares in parameterized square. We show that any string of length n that contains sigma distinct characters can contain at most sigma times n non-equivalent parameterized squares. So there's just a significant dramatically improved. Okay, to prove this result, theorem one, we use another main theorem. So for any string S that contains sigma distinct characters, they can be at the most sigma prefixes of S that are parameterized squares and have no other parameterized occurrences in S. So if we apply this theorem 2 for each of n positions in the strings, so we can obtain this upper bound sigma times n. So in this talk, I will explain, I will show this theorem to proof of the theorem 2. In our proof, of course, we use a periodicity for parameterized equivalent model. So first, I will explain the period in the parameterized equivalent model. Okay, before I explain the parameterized periodicity, so we call that the standard period for string. So this is a definition. So okay, I will show the two equivalent definitions. The first one is an integer p is said to be a period of string w. So if the ith character of w is equal to the I plus p's character of w for all positions. Or equivalently, these borders are there are borders of these ranks. Oh, let's see this example. So this string ABB has periods 3 and 3, 6, and 9, as you can see. And so in the second case, so there is a border of ranks 1, 2, 3, 4, 5, 6, 7, 8. And the length of this string is 11, so this 3 is also a period of this string. Okay, so now I can explain parameterized period by using the standard period. So this is the definition, and integer p is said to be a parameterized period, p period in short, of string w. So there are two equivalent definitions. So if i's character of w maps to I plus p's character by using the bijection f for all position I, or the border-like definition is also equivalent. So this is an example. So this ABBCBABCCAC has parameterized period 6 because so this figure showed that for the second case, so there are okay, so there are both parameterized border. So A, B, B, C, B parameterized equivalent to this suffix B, C, C, A, C by using this bijection. So there is a parameterized period 6. Okay, so we sometimes use this notation by using P and W. So this means that this notation denotes the fact that P is a parameterized period of string W with bijection F. Okay, and also we just write P bar W when no confusing occurs. So we sometimes drop the bijection F. Okay, so to prove our main result, we use the following lemmas about parameterized period. So first one is periodicity extension of the periodicity lemma. The second one is period connection lemma. The third one is the period extension lemma. So in proofs of these three lemmas are omitted in this talk. But I will give an intuition of these lemmas. Okay, let's start from the first lemma. The first one shows the periodicity lemma. So before I will talk about it, so I will show the periodicity lemma for standard period by Fine and Wilf. So this is a periodicity lemma. So let S be a string that has periods P and Q. If the length of the whole string S is larger than this, then the greatest common divisor between P and Q is also a period of whole string S. So in the previous researches, so they extend this periodicity lemma to the parameterized period. The first one is presented by Apostolic and Giancarlo, with SB string that has parameterized period P with bijection F, and another parameterized period Q with bijection Z. So if the length of the whole string S is larger than P plus Q, and this bijection satisfies this condition, namely F and Z commute, so then the greatest common divisor between P and Q is also a parameterized period of S. And most recently, so Ideguchi et al., 2023, they presented another parameterized periodicity lemma without using this commutativity. So they give a condition for holding commutativity by this term. Or let S be the string that has parameterized period P and Q, and satisfied this sigma S means the set of characters that is contained in S, string S. So this means S is not a unary string. So if the length of the whole string S is larger than P plus Q plus this term, then the greatest common divisor is also a parameterized period of S. So we call that this recent parameterized period lemma. So we give in this work we give an improved version of this lemma. We improved this -1 to the -2, and we can see that this term is also tight for binary strings. So because so when the binary case F and Z always commute, so this lemma is equivalent to our conditions. Because this is 2, so this term become 0, so the same statement. Okay, this may be off topic for our research. I will explain our ongoing result for the parameterized periodicity lemma. As I stated before, for the binary case, so this bound is tight, and we have tighter version of the parameterized periodicity lemma for several cases, like this table shows. We can give tight conditions for the parameterized periodicity lemma for the alphabet size is 3, 4, and 4 individually. So we call that we only use this general version in this work. So, okay, I will back to the main proof. So this is the second lemma for the parameterized period. So this second lemma this is the statement of the second lemma that explains the condition for period connection. Okay, so there is three strings x, y, and z, such that P is a parameterized period of x, y with bijection f, and P is also a parameter y, z with another bijection z. So if the length of y satisfies these conditions, so then the P is also a parameterized period of whole string x, y, z with the bijection. So, okay, this lemma says that there are three strings x, y, z, and there is an overlap part, and xy has a parameterized period p, and yz also have p, and they have bijection f and z. So if intuitively, if the overlapping part y is sufficiently long, the whole string has the same period p, and they use the same bijection. Okay, this terms explain the. Okay, if we apply the bijection f around the sigma times, so then y contains almost all the characters. So this is a necessary condition for the period connection. So this is intuitive explanation. Okay, this is the last lemma, the third lemma that explains the condition for period extension from a substring. Oh, this is a statement. So let S be a string that has P period Q. Okay, in this figure, so this S is a whole string and that has P period Q. And S prime be a substring of S, like this. And this S prime has parameterized period P. Okay, so then if the length of the S prime, so the length of this substring satisfies these conditions, this is a sufficiently long length, and this Q is a parameterized period whole string. It's represented by multiple of P. So P is the parameterized square of the substring. So then this P is a parameterized period whole string S. Okay, so intuitively, a parameterized period of a substring which is sufficiently long can extend to the whole string. If the whole string has a parameterized period that is a multiple of substrings p period like this. So this is the last lemma. Okay, so from now on, okay, I will give a proof for our main results. The proof of the sigma prefix 7 by using the three previous lemmas. Okay, we recall that our main results for any string S that contains sigma distinct characters, there can be the most sigma prefix of S like this, that are parameterized square and have no other parameterized occurrence in S. Okay, so S has the 1, 2, 3, and then sigma parameterized squares like this as a prefix. So in this slide, xi, the concatenation of xi and xi prime denotes the i's parameterized square such that xi is parameterized equivalent to xi prime. And x1 is the shortest one, and x2 is longer than x1. Okay. So, okay, let's start our proof for main cell one. Okay, assume on the contrary that there exists a string S that contains sigma distinct characters such that the number of parameterized square of the prefixes of S that have no parameterized occurrences other than the prefixes is sigma plus one. So we assume there are sigma plus one prefix parameterized squares like this. Okay, so since we focus on this parameterized square x1, x1 prime, and x sigma plus 1, because x1, x1 prime has no parameterized equivalent occurrence other than the prefix, so then the length of this parameterized square is longer than the root of this parameterized string. So this equation holds. If not, so x1 parameterized square x1 x1 prime is shorter than x sigma plus 1 like this. So then x1 there is a substring which is that is parameterized equivalent to x1 x1 prime. So by using this bijection, so this is the contradiction. So this condition holds. Okay, so let Ri is the length of this part. So this is I parameterized square, and this is I plus 1's parameterized square. So Ri represents the length of this part. So the length, namely the length of xi plus 1 minus length of xi. Oh, so because of these reasons, we can see that Ri is a parameterized period of xi prime. Okay, so let's see this figure. So xi and xi prime are parameterized equivalent. So because this is a square, parameterized square. So the xi is equal to xi occurs also as a prefix of this xi plus 1, so this green one. And xi plus 1 and xi plus 1 prime are also parameterized equivalent. So this green prefix of xi plus 1 and this blue prefix of xi plus 1 that has length length is the same with xi. So these are parameterized equivalent. So then we have this Ri because this red part and the blue part this difference Ri is a parameterized period of xi prime. So of course, so xi has a parameterized period Ri, so xi also has also Ri as a parameterized period for any I. This implies that x1 uh, uh, this condition holds for any I because each of R is smaller than the length of the root of the first shortest parameterized squares, and x1 is a prefix of xi, like this. So see let's see these figures. So each R is shorter than the root of the shortest parameterized square. So we have we have this one. Okay. For any Ri is a parameterized period of x1. So these are the basic conditions in this assumption. So this is uh, conditions that I explained in the previous slides. So every Ri is the parameterized period of x1, and it is clear that so each Ri is because Ri is a parameterized period of x1, so the shortest period of x1 is smaller than or equal to Ri for any I. Okay, so this is the first main step of our proof. We claim that the smallest parameterized period x1 is also a parameterized period of x sigma. So let's start this proof. Since the condition of the periodicity like this, so we have these equations. Okay, so the shortest period of parameterized period of x1 times -1 plus r sigma is upper bounded by the sum of sigma r's, because R1, the sum of these r's, the smaller than the length of x1 prime, as you can see. So this this inequality holds. This inequality holds. So this term is less than or equal to the length of x1. So this inequality implies that this inequation. So this is a simple transformation. So this one shortest period P is here, and the R sigma stays here. So this term is also upper bounded by the length of x1. Okay, so by using these conditions, use lemma 1. This is periodicity, parameterized periodicity lemma. We apply this lemma for string x1. So because x1 has shortest period P of x1 and also R sigma as a parameterized period. So and they satisfies this condition. This is matched is here, these conditions. So the divisors of P of x1 and R sigma parameterize the period of x1. So since the shortest parameterized period P of x1 is so since this P is the smallest parameterized period of x1, so R sigma is less than or equal to parameterized period P is less than or equal to R sigma, so R sigma can be represented by a multiple P for some integer C like this. Okay, so we can see we can also obtain this equation by using the previous analysis. So we replaced one shortest period P by the constant 1. So this condition, thanks to this condition, we can use the third lemma, parameterized extension lemma for string x1. So Okay, combining with this lemma, and R sigma can represent R sigma is a multiple of the smallest period P of x1. So we have the smallest period of x1 is also a parameterized period of x sigma by using this lemma. So this is an illustration for the proof of this claim. Okay, we call that. So x1 has the shortest period P, which is green one, and also R sigma like this. So we can see that by the equation, R sigma, this blue one is a multiple of the smallest period of x1, which is green one, like this. So this implies that the period P, smallest period of x1, can be extended to the x sigma, like this. So x sigma also has a parameter. So P, the smallest period of x1 is also a period of x sigma. So this is the first claim. Oh, this is the second claim of our proof. The shortest period of also a period of x sigma plus 1. So this claim can be proved in a similar way. So we can analyze this term. We can see that this term is upper bounded by this the length of x sigma. So then we can get these conditions for the string x sigma. So x sigma has two parameterized period P and the length of x1. So we can use this lemma and we can get the greatest common divisor of these two parameterized period is also a parameterized period of the length x sigma. So finally we get the length of x1 is the multiple of the smallest period of x1, like this. Oh, okay. So in a similar way, we can also see that we can get these conditions, and then by combining with this lemma, the parameterized extension lemma, and the multiple representation, we also have the shortest parameterized period of x1 is also a parameterized period of x sigma plus 1. Oh, this is an illustration for this claim. Okay, we got that. X1 has the shortest period P. We can see that the length of X1 is a multiple of this period. So this implies that the period P can be extended to X sigma plus 1 because X sigma plus 1 also have parameterized period, the length of which is the length of x1. Okay, then we can conclude the proof. So we can use the second lemma for x sigma plus 1 here and x1 plus 1 prime. Because so these two green highlighted strings have period P of x1 by the previous argument or definitions. And these strings also overlap each other, and the overlap length is R1 plus the R sigma. So that's the sum of sigma R's. So the overlap length is bounded by distance because each R is larger than or equal to the shortest period P. So, so this lower bound, we can see this lower bound. So by using these conditions, and by combining with this lemma 2, so we can get so this x sigma plus 1 and x1 prime overlap and sufficiently long overlapping. So then the shortest parameterized period of x1 is also for concatenated strings, namely the parameterized square x1 prime, like this. So this x1 prime has parameterized period of x1. So by a similar argument for x1 prime and x2 prime, so they are overlap and they are sufficiently long overlap. So we apply the lemma 2 to here. Then we can get x1, then we can get, so this square, x2 prime, also have a parameterized period of p of x1. So then, x1 prime has another parameterized equivalent occurrence in x2 prime, like this. So we can copy this x1 prime to by using bijection. So there is a parameterized equivalent, and this is a contradiction. So then we can get our main lemma. So we call that for any string S that contains sigma distinct characters, there can be at most sigma prefixes of S that are parameterized squares and have no other parameterized occurrence in S. Oh, okay, so we conclude this talk with several open questions. So this is we call that this is our main lemma. The parameterized non-equivalent square can contain any string can contain at most sigma times n non-equivalent parameterized square. So one natural open question is this upper bound is tight? So how can we improve this upper bound? Or how can we construct a family of strings that gives a good lower bound? So based on our knowledge, so there is no good lower bound for this problem. So for improving the upper bound, so my colleague Rikuya conjectured that the upper bound is n, but I don't know his idea. But for this problem, for improving upper bounds, so there is a simple lower bound for the sigma prefix properties. So this is an example. This is a lower bound for sigma prefixes theorem. So for any sigma, there exists a string with alphabet size sigma, such that there are sigma prefix that are parameterized squares and have no other parameterized occurrence. So this property says this fact says that the previous our main theorem, sigma prefix theorem, is tight theorem. So maybe if we improve this upper bound, so we need somewhat another idea for improving, maybe. And another question is, can we improve bounds in another distinctness? For example, distinct as was. So I have no idea for this problem. Okay, that's all. Thank you very much.
Thank you so much, Yuto. Does anyone have any questions? Oh yeah, Hajime.
So I have a question for, so you talked about the squares. I have a question about analogy for cubes. in
Mhm.
some sense, non-equivalent parameterized cubes. Is it possible to consider such an analogy?
Okay, I've never considered the problem, but mm, maybe, maybe we can use the parameterized period. So somewhat we can apply this analogy. Maybe I have never. So,
Thank you.
Does
uh,
anyone else have a question? So do you think that these techniques will also work in the distinct as words case, or some new techniques are necessary?
maybe so. I don't have an idea how to apply these techniques for the distinct as words. Maybe we need another technique, I think, but I have no idea. So,
Mm,
mm,
thank you.